Which would not happen.
Okay, so good evening, everyone. So how did the exam go? I didn't get any response.
How did it look
Okay.
when grading?
How do you what?
How did it look when grading?
So we are still working on it. I just graded one person's during the class, but during the exam, but it's okay. I mean, I think many of you probably done okay. I think it's it's a learning experience. So as long as you've done better than what you would have done, let's say at the beginning of the class, you should be fine, right? So actually, the TA was discussing some of the exam questions last, in the recitation, and it's going to continue to do that next week. Okay, there were a couple of more questions left from last time. He gave me feedback that one of the questions that was difficult was this question related to LDA and QDA, for example. I think that seemed to be a difficult one for some of the students. So actually, we'll during this class maybe I'll intersperse connections to LDA and QDA, so that maybe it'll become more clearer that concept. Okay. Any questions? No. Okay. Any questions about? I mean, you have your assignment 3 due next week. Okay. Next week also my office hours I'll shift to Monday. Okay, Monday 3 to 4:30. Okay, instead of Wednesday 3 to 4:30. So that's about it for logistics. Yeah.
Is the assignment number 3, you said it's due next Sunday?
I think it's due on 17th. Yes. Yeah. Next week. 17th is what? Okay. Monday. Okay. I might have written it wrongly. Yeah. Yes.
Is the final exam comprehensive or is it just the second?
It's just a second.
Okay.
Yeah. So the final exam is only gonna cover from what I teach today to lecture 12 basically. Any other questions? Okay, so today is actually this is the good time to look at today's topic, because since you have refreshed the first X lectures, first 6 lectures, you know different concepts and how they fit, at least at the modular level. The first few lectures are about linear models, and then towards the end we were talking about maximum likelihood estimation as an idea, as a way to view multiple models at the same time. Okay. So today we're going to talk about a way to approach. The today's lecture has 2 big parts and then one small addition. So the 2 big parts. So before that, one thing which will become clearer today, as an example, is going to be a Gaussian mixture model. Okay, it's just I'll describe what a Gaussian mixture model is. It's just a way to think about data. You might have seen this before, but we'll kind of revisit Gaussian mixture models and generally Gaussian distributions, because those are kind of important ingredients in the in LDA, for example. Okay, the important assumption we make about the probability of X given Y, right? So, but the 2 big parts. First part is going to be what is called the expectation maximization algorithm. So it's an algorithm, it's a technique, but it's trying to, what is the algorithm trying to achieve, right? It's trying to estimate parameters. Just like in maximum likelihood estimation, we are trying to estimate parameters, right? EM will also, at the end of the day, will give us some parameters, okay? But it'll give us parameters to distributions which are more complicated, okay? And the example is going to be Gaussian mixture models. So it's Gaussian mixture models. It's not easy to estimate the parameters by eyeballing things and so on. So there's an algorithm to get us to that, and this algorithm is not specific to Gaussian mixture models. In general, you'll see maybe, I think in this class we don't talk about topic models, but maybe in 572 some of you have seen topic modeling, where you have text and you want to figure out topics of a bunch of documents. So there's this thing called latent Dirichlet allocation. Okay, some name for an algorithm to get this topic, get to know the topics of documents. So to learn the parameters of that model, you actually use EM, but you also use something else. But the core idea is EM. Okay, so so we look at EM. That's one big chunk in the first part. Second part is going to be about sampling. So essentially, we'll look at why do we need to sample first of all, and then we'll look at one example sampling method called Gibbs sampling. We'll probably just go through the procedure. There's a rich background for why such a why a name for sampling and why does it work and so on. Maybe if we have time, we'll discuss it briefly. But so that's a good toolkit to know. Okay, sampling. Okay, and we'll see why do we need to sample. That's kind of more important than how to sample. And the last, I guess, small segment is about generalized linear models. Okay, so linear models is something we've seen quite a bit, and you'll see that generalized linear models is just a name for a slight tweak, and we'll see what the tweak is. Okay, so those are the goals for today. Any questions about the lay of the land? It's fine. Okay. So then Gaussian model or Gaussian distribution. So we'll try to first understand a little bit more about Gaussian distribution, because although we did derive, like we used this for a maximum likelihood estimation problem a couple of lectures ago, right? But it's an important ingredient in LDA, so let's revisit it. Okay. So what's a Gaussian distribution? It's a distribution over numbers. These numbers are not just integers. So in one dimensions, Gaussian distribution tells you the probability of some bunch of numbers occurring. Okay, so we have seen this, right? So let's say in one dimension, probability of a random variable taking a value little x. Okay, in this case, actually, it's a probability density function. Is going to be equal to 1 by square root 2 pi sigma e to the power minus x minus mu the whole square divided by 2 sigma square. Okay, so this is in one dimension. So in LDA, when we make the assumption, so let's say we have one-dimensional data. Okay, and there are two classes. So let's say it looks like this. So there are crosses over here and circles over here. Okay, so all LDA is saying is that condition on a class, maybe the X class, the probability of a feature, probability of X given that class is actually normally distributed. So it's something like this. And given X's, maybe there's a mean with respect to this guy. Let's call it mu1. And for circles, there's also a Gaussian distribution with some mean. Let's call it mu2. Okay, and each one will have its own variance, so sigma 1 and sigma 2. Okay, so that's what the LDA model assumes. So it assumes that class conditional probability is Gaussian. In one dimension, there are like two parameters, two numbers, right, which determine completely what the Gaussian distribution is, because you just need to know the sigma and you just need to know the mu. Okay, then you can find the probability of every point, right? And LDA also has another parameter, which is which distribution the data came from, which of these two Gaussians the data came from, which is just a probability of outcome, which is like probability of g is equal to little g is, right? So maybe little g is equal to let's say 1, or let's say 1 or 2 or 1 or 0 with probability pi and with probability 1 minus pi, because okay, so pi's are just numbers, so let me actually not use pi. Sorry, not numbers, sorry, symbols. Some probability p and 1 minus p. Okay, little p. So we need to estimate. So this is a parameter, and these are 4 parameters. So there are 5 parameters in the LDA model if you have one-dimensional data. Okay, one feature. If you have 10 features, then there will be 10 numbers for mu1 because mu1 will be a 10-dimensional vector. Okay, and similarly 10 numbers for mu2, and instead of sigma 1, sigma 2, there will be matrices. Okay, and the matrix size has to be 10 cross 10 or d cross d. Okay, it's a covariance matrix. Okay, yeah.
How did you get 5 parameters for it?
So
What were those parameters?
So P, mu1, mu2, sigma 1, sigma 2. In this example, LDA in one dimension case, yeah. I mean, this is just a Gaussian distribution. This is just a Gaussian distribution in one dimension. From here onwards, I'm talking about LDA.
Okay.
Those are 5 numbers that I need to estimate if I have been given data. If I know these 5 numbers, then I can find the class of any new data point. Okay. Remember, the log odds ratio is linear in this case. Okay, so the beta log odds ratio is linear, so there is some beta, which is equal to beta, and that beta is going to depend on potentially mu1, mu2, sigma 1, sigma 2, and maybe even p. Yeah, that's all. So is the one-dimensional LDA problem clear? So all I'm saying is, in one-dimensional LDA, probability of x given g is equal to g, little g. This guy is assumed to be normal. So for example, this one or this one, depending on what little g is. For each little g, there is a different normal distribution. Okay.
Would there not be 2 different P's though, one for each different distribution?
There are, so 2 different distributions. Yeah, there is 2 different. Yeah. So I didn't write. Okay, the more cleaner way to write is I said P of x is equal to x given g is equal to g. So for every different g, there is a different distribution here. So for example, P of x is equal to x given g is equal to, let's say, 1 in the previous example, is normally distributed with mean mu1 and variance sigma 1 or sigma 1 square. And similarly, g is equal to 2 is normally distributed with mean mu2 and sigma 2 square. So those are the 2 parameters here for these 2 conditional probabilities, x is equal to x, and probability of g is equal to 1 itself is little p, and the probability of g is equal to 2 is just 1 minus p because they have to add up to 1. Either you belong to one class or the other. There are 2 classes. This is a binary classification problem.
I see.
Yeah. And I think, yeah. So if one dimensions is clear, then I'm going to talk about 2 dimensions, because when I just generalized to, okay, if x is one dimensional, this is how it looks like, and I said if x is 10 dimensional, then I said mu1 is 10 dimensional. Okay, but it's kind of hard to understand like what is 10 dimensional mu1. So there's 2 features, x1 and x2. Okay. So let me just take a point here, and draw concentric circles around it. Okay. So this is a top view. So I'm looking from the top on this plane where one feature is going in one direction, the other feature is going in another direction. These feature values are real numbers, as in like taking values, any value, 1.1, 3.3, minus 2.2, whatever, from minus infinity to infinity. Okay. Then this point would be mu1, this point would be mu2. Okay. So this is a point. So mu1, for example, could be 1 cross 1, and mu2 could be, let's say, 4, 3, let's say, something like that. It's a vector. It's a point on this 2D plane, so it's a vector, right? And what are these concentric circles? This is a top view of that probability density function. So we've seen this top view many times. So if you have a function in 2 dimensions, you can actually just look at it from the top as well, just to get an idea of what the function looks like, right? We did that for residual sum of squares function when beta 1, beta 2 were the 2 dimensions. So RSS looked like some sort of ellipsoidal contour lines, right? So here there's circular contour lines in this example, only because I want to say that P of x is equal to little x1, let's say, yeah, little x. x1, x2, given G is equal to, let's say, class 1. So this is the class 1, this is the class 2. Okay. What do I mean by that? If data comes from class 1, then the data is like kind of points on this, closer to this first lower region, maybe. Like points over here. That's the class 1, and points over here, maybe it's class 2. Okay. I mean, in reality, we've just been given classes. We are just assuming that maybe these classes, there's a Gaussian sitting on top of the first class, Gaussian sitting on the second class, and then fit the parameters of those things, right? So this guy is a multidimensional Gaussian. So this is actually written as 1 by square root 2 pi. I don't remember the formula now. So sigma to the power 1/2. Actually, determinant of sigma to the power 1/2 e to the power minus, let's call this little x vector, which is in 2 dimensions, 2-dimensional, right? X transpose, sorry, not X transpose. I mean, don't worry about too much about the formula, but okay, so it may look messy, but I just wanted to write, what does 2-dimensional object look like? Okay, this thing, what is in the exponent? So what is in the coefficient of that? What is this part? It's just a number, right? So given, so what is this sigma here? It's the parameter, just like the variance in 1 dimension. Okay, it's a parameter of this Gaussian distribution, 2-dimensional Gaussian distribution. In fact, since I drew it circular, sigma, you can think of it as something like identity. So 1, 0, 0, 1 times some value like sigma square. Okay, that's what, because I drew this, the top view of the data looks like, the contour lines are circular. It means that the sigma, which is the variance matrix, I guess covariance matrix, is going to be like that. So we'll have diagonal entries like sigma square, and off diagonal entries zeros. Okay. Contrasting it with a case where if these things were not circular but ellipsoidal, then there'll be some off diagonal entries, something like A, B, C, D, whatever. So these off diagonal entries will be the covariance of the first random variable with respect to second random variable. So this really, in 2 dimensions, Gaussian, the first coordinate is also as a random variable, the second coordinate is a random variable. They covary together, okay, and there's some covariance between them, and that covariance entries are going to be in the off diagonal entries of this matrix sigma, which is the covariance matrix. Okay, the diagonal entries will be the variance of those 2 random variables. Okay, in this case, two coordinates, 2 random variables. And the exponent is something like x minus mu transpose sigma inverse x minus mu. The reason why I write this is only to say that this number evaluates to a scalar. Okay, so that nothing is breaking here. So if it's 2-dimensional, this is 2-dimensional 2 cross 2. This thing is 2 cross 1. This thing is, because of the transpose, it's 1 cross 2. So the whole thing evaluates to 1 cross 1. Okay, just saying that, okay, there's some formula, it's consistent, given, it can tell you what's the probability mass function for a value little x1, little x2, for example. It'll evaluate to some number. And with dense, probability mass functions, or probability density function in this case, if you integrate it over the whole values that x can take, in this case minus infinity to infinity in 1 dimension, and the second dimension minus infinity to infinity, then that integration should be equal to 1. Okay. So this is a 2-dimensional Gaussian. So in LDA, when we said features can be d-dimensional, we can't really visualize them, but they are d-dimensional Gaussians. Very similar spirit. Okay, sigma is now, instead of 2 cross 2, it will be d cross d. Okay, and So sigma now, instead of, you know, previously, for example, this is like something like sigma square 0 0 sigma square. This one only has one parameter because I drew circles, but if there are ellipsoids, then there are 4 parameters here, right? 4 parameters, and you will see that C is equal to D, so it's symmetric. So, you know, covariance, you know, how A varies, you know, how x1 varies with x2 is the same as how x2 varies with x1. It's a symmetric thing in conceptually, and so there are few little lesser number of parameters. Okay. So does anybody remember the covariance definition? Covariance of 2 random variables, covariance of, let's say, W and Z. Let me use the next sheet actually. Is the expectation of W minus the expectation of W times Z minus the expectation of Z, right? And correlation is just renormalize it with the individual random variables, you know, variance, or basically the standard deviations. Okay. So this is the covariance of 2 random variables. So I'm just saying that the off diagonal entry in the previous example was, you know, this example, for example, A and B, sorry, not A and B, C and D, for example, are just those evaluate, you know, you evaluate these guys. I mean, there's something like this, evaluation something like this. Okay. For the first coordinate, instead of W, write the first coordinate capital X1. Instead of Z, write the second coordinate capital X2. Okay. Just giving it, I don't want to confuse ones who already know this, but just to give you an idea of how does a higher dimensional Gaussian look like, 2-dimensional Gaussian. Okay. So top view is kind of very handy to get conceptual understanding of Gaussian. So you could have a Gaussian like this. Okay, single Gaussian. Now forget about LDA. Have a single Gaussian. Yeah, there I drew 2 Gaussians, but if there's a Gaussian like this, then I mean it corresponds to some sigma, right? Some covariance. With the center of this concentric circle being the mean. Okay, so think of a upside down bell, basically. That's the mean, and it's going down. Okay, as something which is like e to the power negative. Oops, sorry. Something which is e to the power negative some quantity. So you'll see that when x's are large, then the value of this p of x is going to be really small. So it's like really an inverted bell. Okay, so that's good. So what I wanted to actually do was talk about mixture of Gaussians. Okay, so let's say there's another Gaussian here. Okay, so there are 2 Gaussians, only top views, just conceptual understanding. What do I mean by mixture of Gaussian? Okay, let's call it. Okay, mixture of 2 Gaussians is just, as I said, yeah.
Just so I can get the visual right.
Yeah.
The lowest point on these contour lines is the center point, right?
No, highest in this case.
And with the z-axis coming toward us being what?
Is the probability density function value. Okay. This function.
I see.
Yeah, it's like literally the probability mass function. Okay. So it's think of it as a bell and chopping the bell. I got this concentric circles. I just projected it down into the 2D space. Okay. The highest point is the central point, the point in the centers. So these are 2 Gaussians. A mixture of Gaussians is just nothing but a distribution which will have 2 bumps. Okay. Well, the first bump is over here. The second bump is over here. Okay. So mixture of Gaussians is just this, but there is a little bit more description, which is like there's a little bit more to it, which is very parallel. It's a parallel with the LDA idea, which is that. So let me write down the description. So I'll call it the generative description, and then other ways to describe it as well. I'll start with the generative description, which is first I'll get a value delta, which is Bernoulli, with some parameter pi. So this pi is not 3.14. It's just a symbol. Yeah.
So you said like mixture of Gaussian designated for two classes. That's the distribution, or just like
There are no classes now. So till the last page, we were talking about LDA a little bit. So the last page, there were two classes, class 1 and class 2 in the square boxes. So I said, if you want to think of this conditional probability of x equal to something given the class it's a Gaussian. Okay, so that was just to designate what does it mean, what does the LDA assumption really mean. In 2 dimensions you can just think of this Gaussians, 3 dimensions is also Gaussian, 10 dimensions is also Gaussian, but you can't really visualize it. That's it. So LDA story is done. Now I'm just describing what is meant by mixture of 2 Gaussians. Okay, it's a different it's basically the same objects, 2 Gaussians, let's say in this case, but there is no classes here.
okay, so we just have. Then what is the dimensional third one? Like you have.
This is a density function. Always it's a density function, right? It's just a density function. It's like 2 hills. Okay, one hill is at maybe 2 cross 2, and the other hill is at like 3 and minus 1. Let's say. That's all.
Is it a bimodal distribution wherein you have
Yes. So the question is whether it's a bimodal distribution. Yes, we're gonna. So Gaussian mixture model will typically be bimodal, or if depends on the number of mixtures. But yeah, it's basically a bunch of hills. Yeah. So bimodal just means 2 peaks. Original, the Gaussian distribution that we saw, in general, whether it's k dimensions or 1 dimension, it will have 1 peak. 1 dimension, everybody knows, it's just 1 peak. Even in d dimensions, a single Gaussian distribution will have 1 peak at its mean. Here, there's a distribution that I'm trying to describe, which is the Gaussian mixture distribution, which has 2 peaks. Okay, 1 peak at let's say 2, 2, and the other peak at 3 and minus 1. Okay, and I'm just describing the distribution in a particular way, which you will see. So this way you will see even in that more complex thing that I was talking about, latent Dirichlet allocation. So topic modeling, there is some associated generative description. Okay, just to give you a hint towards the future. We'll not look at it today, but if you come across it, it's the same way. Okay, so here what's the generative description? I first draw Bernoulli, so it will land heads or tails. That's written by capital delta, so it takes a value heads or tails. Depending on whether it takes a value heads or tails, I'll draw a distribution y1, okay, which is normal with mean mu and variance sigma 1 square. Or I'll draw a variable y2, again with mean mu2 and sigma 2 square. Okay, the description is very similar to LDA description. In fact, it's the same generative description for the LDA as well. Okay, but I don't want to confuse you. It's the same description, but let's ignore LDA for now, because we are not really thinking of classification. I'm just trying to describe a bimodal distribution. Okay, there's a generative way of thinking about a bimodal distribution. Maybe I first pick which peak I belong to, and then I draw a sample from that peak or that Gaussian distribution. That's a way to say that this is a Gaussian mixture of 2 Gaussians. Okay. So when I said first I pick delta and then pick a value, it's as good as saying y is equal to let's say 1 minus delta times y1 plus delta times y2. So when delta is heads or delta is 1, then this term is 0, so y is equal to y2. I got the number from the second peak, and if delta is 0, then I lose the second term there, and so I get a number from the first peak or first Gaussian. Okay, that's the Gaussian mixture model. Any confusions at this part? So you may think, okay, why are we talking about Gaussian mixture models, right? If you have continuous data, let's say tabular data, continuous data, okay, you can actually do clustering by fitting Gaussian mixture models. If you think there are two clusters, you'll fit two Gauss. You can think of two clusters corresponding to two like high probability regions of two Gaussians. Yeah.
My question was back a little bit.
Yeah.
Sorry. You said that we shouldn't think of this as a classification problem.
Because there is no classes here.
It is a Bernoulli problem, which is either heads or tails, and so the variable, the mean is going to be like the number of flips you get before you get a.
No, that's so Bernoulli is not about. I mean, I think you're confusing between Bernoulli and geometric random variable, but let's not worry about geometric random variable, which is the number of flips before you get a first heads and so on. Let's not worry about it. Bernoulli is just I flip a coin whether it's heads or tails. Heads with probability pi, tails with probability 1 minus pi. Pi is not 3.14. Pi is just a symbol here. Okay, this is a generative way to describe a distribution which has two peaks. Okay.
And each one of those peaks would be the heads, and the other peak would be the tails.
Yes.
And
Yes.
so, how do you do a distribution around heads?
So I don't understand the question properly, but
So it's either heads or tails. So how is there going to be a probability distribution around heads only?
so condition on heads, there is a distribution which is the, let's say, the top one. So this thing, so it's so in a Gaussian mixture model there is there's no need. So the heads and tails is just a generative way to say this. What I observe is just y's, right? I just observe some points on this 2D plane. Okay, there is no really capital delta. Okay, which is that Bernoulli thing, whether heads or tails. There is no really such thing. I'm just saying that I'm gonna hallucinate about, if my data has two peaks. Let me give a clearer example. So let's say you had a bunch of data points in one dimension. Forget about classification. Now it's just some data, exploratory analysis. I've gotten a bunch of data points, and I drew a histogram. Okay, and I got a histogram like this. Okay, so I got a histogram like this. I can't fit a Gaussian here, right? It doesn't look like a Gaussian at all. So I want to fit. So the next natural choice is fitting a Gaussian mixture. Okay, which means that my distribution has to look like this. Okay, a Gaussian mixture model that I described in the previous slide corresponds to this type of a two-peak distribution. Okay, because each component is going to be Gaussian. Okay, the Bernoulli thing is just is a parameter of this distribution. Okay, but it doesn't, you don't visualize it. So my data is, whatever it's called, let's call it x. Then this is the distribution p of x is equal to little x. Okay, it's bimodal, but I'm saying that actually I should have used bi, but this model can be described using hidden object, which is that Bernoulli. Okay, I'll make it more clearer in the next few steps, but at this point, this generative description that I was talking about is essentially the same description you would have seen when you looked at LDA. Okay, so LDA is essentially saying class condition on a class, it's a Gaussian. Okay, the class can be heads or tails or 0 or 1. So for each class there's a Gaussian. Okay, here it's almost the same. It's basically saying, let's say there's a Bernoulli delta. Let's say there are two Gaussians in my data. From both I'll get the samples, but the thing that I observe with the actual y is just 1 minus delta times y1 plus delta times y2, which means that when delta is heads or tails, or in this case 0 or 1, you'll only see the first one or the second one. Okay, that's just a way to say this is how maybe data was generated. Maybe data was not like that, but there's a model for the data. Okay, is a one-dimensional example clear? So what we are trying to do is model these types of distributions. Okay, I mean there's no name for this distribution, right? This looks, has two peaks, or it could have 10 peaks, 10 different components. So these types of multimodal distributions, which could have multiple peaks, we can think about some sort of a mixture of basic components, and in our case the basic component is going to be a Gaussian distribution. So we'll think of, okay, maybe it's like two Gaussians somehow. I can model two Gaussians somehow to get to this bimodal distribution as the output. Okay, so the actual, if you ask me, the actual distribution is actually let me make it y, okay, just to keep everything consistent. Y is equal to little y. So probability of y is equal to little y is 1 minus pi times probability of okay, actually 1 by square root 2 pi sigma 1 e to the power minus y minus mu 1 square by 2 sigma 1 square plus pi times 1 by square root 2 pi sigma 2, same thing, e to the power minus y minus mu 2 square by 2 sigma 2 square. Okay, so this is the actual distribution, which means that at any given y, let's say over here, let's say y is equal to little y, I can just compute this number. So I know pi, let's say I know pi mu 1 sigma 1 mu 2 sigma 2, I can compute this number. Okay, hopefully the parameters are such that it will evaluate to something like this. I mean, if I know the parameters, it will evaluate to something, and that will look like a 2-mode thing. Okay, so this is the distribution of my data, the thing that I observed. Okay, so in this description there is no notion of a Bernoulli or anything. It just looks like averaging two Gaussian probability density functions, but that looks messy, so we're gonna that's why we talked about first flipping a coin, getting heads or tails, and then depending on that, getting the y value. Okay, it's the same. So you can see that if this is the probability density function, now think about maximum likelihood estimation, right? If you were doing maximum likelihood estimation for a single Gaussian, you would have a data point little y or few data points, let's say 100 data points, and to maximize the likelihood of the data, you will try to find the parameters, and you will see that if you take the log likelihood, log and exponent cancel, and you just get some sort of a squared, negative squared as your term to maximize, or the positive squared to minimize, positive squared term to minimize. Okay, here, okay, I said that verbally, so all I'm saying is typically MLE, you want to maximize the likelihood, which is think of log likelihood, and sum over I is equal to 1 to n of the log of the probability of y is equal to little yi, right? I observed a bunch of data points, y1 to y100 data points, one dimensional, let's say one dimensional, just for, it doesn't have to be one dimensional, but for simplicity. Then this is the likelihoods. There's a parameter theta. Okay, I have observed these data points, I don't know what the theta is, I want to figure out the theta that maximizes this thing, which is the log likelihood. Okay, and sum is because I took a log, otherwise it will be a product of probabilities. Okay, this you have seen because you studied for the exam. If this was a single Gaussian, it's kind of easy, log and e to the power minus something, the log and e to the power something cancel. Okay, but if you saw the previous expression, right, there is e to the power something, which is the first term, plus e to the power something else, which is the second term. So here log and e to the power don't cancel. Okay, what I'm saying is log of e to the power a is a. Okay, log to the base e of e to the power a is a. But log of e to the power a plus e to the power b, you don't know how to deal with this. Okay, that's the only that's a big change actually, and this motivates using some other algorithm. So in MLE, if it was it's a single Gaussian, you would get basically MLE is the same as minimizing over, let's say I'm estimating mean of yi minus mu the whole square, sum over I is equal to 1 to n. Okay, this is what you would get, and you know what the mean is. It's just the average of the yi numbers. Okay, but if you want to do MLE for the Gaussian mixture, which is that distribution that we saw, which doesn't have to be 2 modes, it can be multiple modes. It's not clear how to do this, and that's the motivation for maximum likelihood estimation. Sorry, that's the motivation for expectation maximization algorithm. Okay, so the problem is fixed. We want to estimate the parameters of Gaussian mixture model. There are 5. How many parameters are there? Same like LDA. There are 5 parameters. Sorry. and that there are 5 parameters. Okay, in the previous slide you saw, right? So sigma 1, mu 1, sigma 2, mu 2, and pi. Very similar, it's essentially the same as LDA actually, without the class idea at this point. I mean, here there's no second random variable, so there's no class here. Yeah.
Really, we cannot calculate y for multimodal distribution because in y
We can calculate probability of y is equal to del y. That's fine, right?
What about y wherein we calculate using delta? Like you took either one
Yeah.
or two, right?
Yeah.
0, 1. So
Yeah, y's can be, I mean, this doesn't have, so these can be multi-dimensional. Sorry, these two, y1, y2 can be 2 dimensions, 10 dimensions, that's fine. If there are 10 dimensions, let's say y1 and capital Y1, capital Y2, let's say 10 dimensional Gaussian, then it will be 1 minus delta times that vector plus delta times that other vector. So delta is just a scalar, I mean, it's 0 or 1. So it's like picking one vector versus the other.
will be a 0 at that point.
No, delta is scalar, right? So it's just, I'm multiplying a vector with a 0, then the whole vector is 0, right?
I'm not saying that. I'm saying if I'm using more, here you're taking in just y1 and y2. If you're using y1 till
Y2, yeah. So there could be 5 classes. So his question is about 5 multiple classes, more than 2 classes. Yeah, that's fine. So delta doesn't, so this is not the way to write this then. Yeah, then first of all, delta will not be Bernoulli. If there are 5 classes, then it's called a categorical distribution. Okay, it's just like a probability mass function where there are 5 values that it can take, right? Instead of heads and tails, let's say think of a die, right? It will take 6 values, right? 6 different values. So it's just a probability mass function. So this is not the description for more than two mixture components. Yeah. And before that, I was just motivating why we are looking at Gaussian mixture model, right? It's because of clustering. So you can, if you know this tool well, you can do clustering as long as the data is continuous. Okay. I mean, all the features are continuous. Let's say 10 dimensions, all of them are continuous, then it's fine. Okay.
When I have even let's say Gaussian, right? I can have a uniform distribution also like a bumps, right? Can I have something like that?
This is a Gaussian mixture model. You can mix any set of distributions. That's fine.
So the basic idea is throw any data, find the bumps in the data, and that can be classed as some sort of like clustering or something like that.
No. I mean, so what's your question? So let's say you've been given a data in a workflow.
Yeah.
Then what do you want to do?
Assuming so, it's not a Gaussian. So
yeah, sure.
it could be some uniform distribution. Then it's coming down, and then again one more sort of like a uniform distribution. So
It could be a mixture of any. I mean, so Gaussian mixture models assumes the two components are Gaussian, but you can have mixtures of multiple distributions, multiple different distributions. You can. So if you understand this, then you can change the distributions and be confident about them. But if you don't understand this, then yeah. But you're correct. I mean, we can change the distributions. Yeah. Any other question? Okay, so let me tell you what we're going to do. We'll try to. We saw that with this distribution P of y, we can't really do MLE, so we're going to do expectation maximization. Okay, it's a name for an algorithm, but what does it do? It's gonna assume that so the intuition for this algorithm is that just maximizing P of y is equal to y, it's hard because it's like something like this in each term of the likelihood function. So I'm gonna try to somehow address this by saying, what if I had the not just the y's, okay, not just the yi, but also some other values which are delta i's. Okay, what are these other values? These are scalar values, as in numbers. These values are actually the 0, 1 values of the Bernoulli. Okay, there is this Bernoulli, right, which is not there in my data. My data is just y's. Okay, I'm gonna hypothesize or just just intuit that maybe I can think of a hidden or a latent variable delta that corresponds to each of these observations. So for each little yi, I have a realization of a Bernoulli random variable which tells me which class it belongs to. Okay, I'm just going to hallucinate. I don't have the data. I can always fix some data right there. So I'm going to assume this is my data. Okay, and with this data I can actually define a different likelihood function if I have this additional point, okay, which is probability of y is equal to little y and delta is equal to little delta is log of the probability of y is equal to little y, let's say with mu1 sigma 1 to the power 1, okay. Probability of mu1 sigma 1 of y is equal to little y to the power 1 minus delta times probability of mu2 sigma 2 y is equal to little y to the power delta. So what is it doing? If delta is 1, I'm going to pick the first term. If delta is 0, sorry, if delta is 1, I'll pick the second term, okay, because delta is 1, the first term is 1 minus 1 to the something to the power 0 is gone, okay. So if I had data, so let's say yi came from the second component, I'm just picking the probability density function related to the second component, okay. And if it comes from the first component, I'm just picking the probability density function for the first component. This is a very convenient way to write it, okay. So if this is now the joint probability, right? Probability of one random variable taking one value and the other random variable taking another value, okay. For this guy, if I take the log likelihood, you can see that if you take the log of that probability of y is equal to y comma delta is equal to delta, you will see that, and let's say there is yi and delta I, so for a particular observation, and I sum over i's, okay, average over all the data points I have, 100 data points, then this just corresponds to sum over 1 minus delta I of this probability which depends on mu1 and sigma 1, actually it's a log of the probability which depends on mu1 and sigma 1 and then yi's plus delta I times log of the probability of mu2 sigma 2 of yi's, okay. This whole thing in the summation. So all I'm saying is I just took the log of that term which this log of this underlined thing. If you take the log, then log of a times b is log of a plus log of b, and log of a to the power x is x times log of a, okay. These are some basic facts. Yeah.
Tell me if I'm asking too many questions.
No, let's go ahead.
So delta in that equation that's second from the bottom is essentially telling you which of the Gaussians we have under focus.
Yes,
correct?
yes.
So how do you convert that to a number that you will use to raise the probability to a power?
So I'm saying, a mixture of two Gaussians, delta is only taking value 0 or 1. I'm saying that this delta is only either 0 or 1. Good question. Okay, Bernoulli. Yeah. Okay, so we hallucinated, let's say if I had additional data, this little delta is, then the likelihood this is a different likelihood. It's a likelihood of two random variables taking two values. But that guy, if I take the log likelihood, it gives me two terms where somehow, the two terms somehow I could deal with the log and let's say like here, I could deal with the log and the probability of mu1 comma sigma 1 of yi, which is the first Gaussian. There's an e to the power something. So log and e to the power again cancel. Okay, it's the only reason why I introduce new deltas is to cancel log and e to the power. And so the first term would be similar to the MLE of a single Gaussian, like with this additional 1 minus deltas in there, okay. And these deltas are, let's say, data which I don't have so far, but I'll tell you how to get the data, okay. So if I had this additional data, latent data, that's what it's called typically. Yeah.
So how does it handle overlapping data where you have a data point that is falling under both the Gaussians, if you either have only 0 or 1, one of the terms is going to completely cancel out.
Yeah, so data can be here, right? So we don't know whether it came from this Gaussian or this Gaussian.
So it came from both, right?
No, in this model, it might have come from one of them. How can it come from both?
Oh, I see. Yeah, okay.
So, yeah. So first we were in the addition, like I had the same doubt because in the addition.
In this addition? Yeah, I mean, only one of them will
We
be.
were assuming that the whole landscape is like an addition of the two landscapes, right? The values are.
It is an addition. Yeah, it addition such that it sums to 1. Yeah.
Yes, but now we are assuming that given one distribution.
Yeah.
Like we are not taking into account the second one, right?
We are not. Yes.
We are not, right? So,
Sure.
So there's a difference. It's like superimposing two Gaussians. It's just taking one Gaussian.
But isn't this the hypothesis that we
Okay.
every yi we are assuming either of the one of classes, right? In a 2
But
class.
how
form.
is it
Yes. Let
combination?
me tell. So his question is, okay, how am I somehow ignoring the second component? So there is no inconsistency. Okay, if you look at this joint distribution between y and the Bernoulli, that's what it is, right? In the generative model, I said flip a Bernoulli and then you get first component and second component, which essentially corresponds to this, the underlined thing over here, this thing over here. If you take the marginal, okay, which means that marginalize out the delta, which means that sum over the two values the delta takes, you will get that distribution, which is the average, just something like this. And you can see that, okay. So this is the same distribution. I just added another random variable, so I have additional degree of freedom, and because of that, I could think of it that way. Yeah. So what's your question? You don't have a question, but you were answering his question.
I thought our hypothesis was based on that.
It's a generative view of the. So the data is just this, right? 2 peaks. I don't know. I mean, given that there were 2 peaks in the histogram, I'm thinking, okay, maybe there are 2 Gaussians. And now I'm, I guess, hypothesizing or like thinking of, okay, what is the parametric distribution I should fit? I should fit a mixture of 2 Gaussians. There'll be.
Delta is basically an assumption on yi, right?
Delta is a random variable which is not there in the data. I'm going to hallucinate about it and basically fit the parameters of my mixture of Gaussians, because the mixture of Gaussians will have parameters for the 2 Gaussians and this pi which splits between them. By kind of thinking, hypothetically thinking that I had additional data, I can work with likelihood functions easily. Okay, but ultimately my goal in the EM or whatever ultimately is to get the parameters of the Gaussian mixture model, which is the mean, the variance of the first Gaussian, mean and variance of the second Gaussian, and the pi. Okay, that's the goal. Whatever we are doing in between is to get to that goal. Okay.
I'm sorry, can you go back to the last graph?
Yeah.
The point at the very bottom in the center there?
At the bottom, yes, here.
Yes, the point there on the actual curve itself, which is higher than where you've drawn, correct?
Okay.
That is not on one or the other of the Gaussians. That's a combination of the 2 Gaussian curves.
Yeah. So if it was from the first Gaussian, so okay, let's understand this curve. So zoomed in, okay. So there's some Gaussian which is going like this, some Gaussian which is going like this. It doesn't go to 0 actually, but okay. So that curve is something like this. Okay, this is the real. This is this curve. Okay, the ones which I drew are like if I had 2 Gaussians. Okay, now you're saying that the probability mass for a point over here, let's say, is higher than each of the Gaussians.
Right.
Yeah, that's because if I see that point, I don't know which Gaussian it belongs to, so I have to add the probability mass of both of them.
In the formula, though, you had either a 0 or a 1, so one of those probabilities is going to be.
No, the probability mass of that point. So, probability mass of that point is the first Gaussian's mass with a multiplier, which is let's say 0.5. Let's say pi is 0.5. Okay, so it's 0.5 times the probability mass from the first Gaussian plus 0.5 times the probability mass of the second Gaussian, both added.
That I get it there.
Yeah, that's over there.
On the next page that doesn't make sense.
Oh, the next formula is for a different distribution. It's not the marginal distribution. It's not the probability of y itself. It's the probability of y is equal to y and delta is equal to delta. It's a different different probability. Yeah. Okay, so we're going a bit slow. So Now I said, okay, if we had delta, then we would think of doing something with the joint distribution so that the problem becomes easy. Likelihood maximization problem becomes easy, but we don't have deltas. Okay, we don't have deltas at all. The data is just y's. Okay, so what are we going to do? So we're going to do this. Y1 to yn is the data, right? And we'll also think of our parameter set to be this. Okay, mu1, sigma 1, mu2, sigma 2, and pi. Okay, there are five numbers here in the one-dimensional case, but you can think of higher dimensions the same thing. Higher dimensions just means these guys are replaced by sigmas, and mu's are the same symbols, but they're vectors. Okay, but it doesn't matter. So what we're going to do is as follows. We'll start with some theta naught. Okay, so data is fixed. Let's just hallucinate, or let's just start that, say that, okay, maybe first mean is 1 and second guy's mean is 2 and variances are the same and pi is 1/2. Let's say we start with something. Okay, if we start with that, then we can actually find, I mean, this is parameter of this random variable of this joint distribution, right? I mean, when I say theta completely determines this joint distribution. That's the parameter of that joint distribution, right? So because I know theta naught, I start with I just assume something. I can compute probability of delta is equal to delta I given y is equal to yi. Okay, I can compute this under that theta. I mean, given the parameters, if I observe little yi, tell me what the delta is, I can compute this. This is just a conditional probability. If I know the joint distribution, I can compute everything, right? Right. So I compute this, 1 per observation, and because I don't know the delta values itself, instead of deltas, I'm going to replace these probability values. Okay. So in that previous expression, the one at the bottom, sorry, I mean, it's a big mess here. So in the previous expression, there was 1 minus delta i's. Instead of the delta i's, I'm going to substitute this guy. Okay. So deltas are exactly either 0 or 1. This guy is going to be between 0 and 1. It's a probability value. Okay. So I have my data that's fixed. I start with some assumed parameter of my Gaussian mixture. Given that assumed parameter, I'll get this conditional probability of delta is equal to little delta I given y is equal to yi. I can compute that for every observation. I'll use that in my likelihood expression, right? But these are some specific values, with some numbers between 0 to 1. But likelihood is still a function of theta. Okay, that see in the previous slide, it's still a function of this guy, mu1 sigma 1, mu2 sigma 2, and it should also be a function of okay. Okay, that's fine. It's a function of mu1 sigma 1 and mu2 sigma 2. Okay, so I can find mu1, that's a new, mu2 new, new as in like new values, sigma 1, sigma 2. I can also find a new value of pi. Okay, I'm just putting 1 at the top just to say that I did not have deltas. I assume some starting value, got some proxy numbers which are between 0 to 1. I'll plug these in instead of the deltas. I'll have a likelihood function which is still a function of parameters. I'll maximize that likelihood. That's easy to get new values for mu1, mu2, sigma 1, sigma 2. If I know mu1, mu2, sigma 1, sigma 2, I can also find pi. Okay. Pi is just the I mean, there's an expression for pi, but pi is just a number of points belonging to the first component divided by all the points. Okay, so there is an estimate for pi as well. So I got these numbers. So what I'm going to do is again repeat the loop. Now I have this whole thing. I'm going to call it theta 1. Okay, so I got some new bunch of parameters. with a new bunch of parameters, again I'll estimate new values for what is the probability of delta is equal to little delta I given y is equal to yi. Data is fixed, but the deltas are what I don't know. I'll get potentially new values because the thetas have changed, the parameters changed. And once I do that, again I substitute into likelihood, again get some new values, again repeat. Okay. Is the loop roughly clear? Okay. So this is EM. Okay, yeah.
So do you select which one maximizes the most after doing all the loops, or?
No, this is the maximization step. So no, so essentially what's happening is it's an iterative procedure. I'll start with some parameters. So that's why I was superscripting it with theta with 0, right? So I start with some parameter value, these 5 numbers, get to next parameter values which are 5 numbers, get to another set of parameters which are 5 numbers. Think of it like gradient descent, right? I started with some parameter, another parameter, another parameter, another parameter. Eventually, after let's say 1,000 rounds of this, doing this, I'll get to the final bunch of 5 parameters, and they are hopefully the best parameters. Okay.
And to clarify, on the first step, you're only estimating the probability of delta given those parameters. That's all you're doing at the first step, right?
Probability of delta is equal to little delta I. Yeah, I mean starting. So given any parameter, I can estimate such conditional probabilities. Okay. Estimate these conditional probabilities, put it into the likelihood that I defined in the previous slide instead of the deltas, because I don't have the deltas. That's why I'm doing this. And then it's still a function of the parameters. You know, from parameters I went to some numbers. From numbers I can go to the likelihood, plug in those instead of deltas which I did not know. Plug in these guys, the ones in the star, and optimize, and I'll get these parameters, new parameters. I use the new parameters to again compute these conditional probabilities, plug it into the likelihood, again maximize likelihood. Okay, so EM, the M part is here. Okay, M part is just maximizing the likelihood. In every iteration, maximize the likelihood as a second step. The E part is the expectation step, which is this. Okay, the one which is star marked. Okay, this is the expectation of things that I did not observe. Why is this expectation? Because it's Bernoulli probability of y is equal to 1 is the same as the expectation of that random variable. Okay.
Even these parameters are a little bit biased because you are obtaining these parameters because you are assuming something for the theta naught.
Yes. So his question is, are these parameters somehow biased? Bias is not the right word, but there is some sensitivity to initial condition. Initial starting point influences where I end up. Okay. That's because that's true, and so EM is actually an algorithm or an iterative procedure to get to something called a local optimum. Okay, locally best parameters. It will not fit the best parameters which you can eyeball for that, let's say, mixture of two Gaussians. Okay, and that's because the original problem had the likelihood function like this, right? So the original problem is actually something called non-convex with respect to its parameters. So it's basically like a bunch of hills and valleys. If you look at the likelihood function, okay, not the parameters, the likelihood function is non-convex with respect to its parameters, those 5 numbers. Okay, in 5-dimensional space, something like hills and valleys. So you don't know where to. Algorithms in these types of local iterative algorithms, they'll only get to some valley or hill depending on what you're doing. In this case, it's expectation maximization. We are trying to get to the top of the hill. We may get to a locally optimal point. Okay. Any other question? Okay, so there is in the notes there is a figure which explains the EM algorithm for Gaussian mixtures. Okay, there's a lot of details about what were the estimates at every step, but that's not very important. The first important thing is we did not have the original likelihood function was bad. We added some hallucinated data, and we did not have the data, so we added some expectation of what would be the expected value of the data for a previous set of parameters, which was theta naught in this case. Given a current candidate parameters or previous parameters, I would have an expected value of what would this unseen data would be, and then plug that data in and actually have the total likelihood, so you can maximize parameters with this full new joined data. Okay, so that unseen data is called latent data or unobserved data. Okay. Any questions? Okay. So EM, So there's a figure 6 in the notes which gives the EM algorithm. So you start with some theta naught. Okay, in the E step, you compute I'm saying you compute something called the conditional probability of Zm given let me use Z and theta. Let's say theta naught. Okay, and in the M step, you maximize over theta of average out the Zm, probability of Zm given Z and theta naught of that likelihood, which is the likelihood of given both Z and Zm. So okay, what are these? There's several symbols here. Theta is the same bunch of parameters. Okay, I start with theta naught, estimate what are the basically I estimate either the expected value or the probability of the unseen data. So Zm means missing, M means missing. So I estimate the probability of the data that I did not see given the current parameters, because I can always do that. Once I compute this number, I can use that number. Okay, this likelihood needed actual data, but I don't have the data, so I can use the probability that the data took value something, value A, value B. I can average it out, and this part is the missing data. So the missing data and the given data. So the yi's and deltas. So this is C is like yi, and actually y and Zm is like delta essentially. Okay, so this is the likelihood which is easy to solve. All I'm saying is EM step. This part is what's easy because this likelihood is easy. We saw that, and so you'll get some theta 1. So let's call this from here I get theta 1. Okay, and then again I use theta 1 again in E step to get probability of Zm given Z and theta 1, and again in M step I do the max over theta of the same thing with the theta naught replaced by theta 1. Okay. That's all. Now this is the procedure. It's an iterative procedure going from theta naught to theta 1 to theta 2. Why is it maximizing the, or why is it helping me find the local optima of the original problem, which was the original problem is maximize over theta of the probability of Z given theta. Okay. Original problem is just this. Z means so as I said, Z is just Y in the mixture model problem. Okay. So why is this helping me to maximize this? Okay, we'll try to answer that in the next 5 minutes. Okay. Any questions about EM algorithm? Because I'm going to now explain why it works. In a sense, it's doing something iteratively, but we care about maximizing this, which was the original problem, non-convex problem. Why is it at least getting to the local optima? This iterative procedure getting to the local optima, because it's not even maximizing. We want to maximize this, but it's not. It's maximizing something else, right? This huge underlined thing. It's maximizing something else. Yeah.
Maybe it's not as important, but is there any framework for choosing or assuming the parameters initially?
No, it depends on, so your data, so your model, so this, any choice for assuming theta naught, you're saying, the first starting point?
Yeah.
No, it depends on each model. So mixture models, there'll be some theta. And as I said, this procedure, the reason why I'm going through the gory details is because you'll come across topic models, you'll come across Bayesian versions of linear regression and so on. So there are many conditional random fields. There are many different models that you may come across in your professional life. But underlying all that is some likelihood which is hard to optimize. And so people have invented tricks to work with some slightly different likelihoods which are easy to optimize, which will typically appear in the M step and still get to good parameter values for your problem. Okay, so whether it's topic modeling or text processing, conditional random fields, or in this case, I guess, mixture of two Gaussians. Okay. So let's in the next 5 minutes quickly go through what is why does EM work, and for that log of the probability of z given, let's say, theta prime. I'm going to use theta prime. So this is my likelihood, my actual likelihood. Z is my data. Okay, I just changed the notation from y and delta to z and zm just to keep it general. Okay, so if you want to think of it, think of z as y. Okay, so you have this. This is the likelihood that we care about. Okay, and this is actually equal to the log of probability of z and zm given theta prime minus the log of zm given z theta prime. Oh, actually there's probability. Why is this true? This is by just a definition of conditional probability. Okay, so probability of z is, I mean, if I drop theta prime, it's just a parameter, right? So just for simplicity, I'm just suppressing the notation. It's just the probability of z and zm divided by probability of zm given z. Okay, you can bring the denominator to the left hand side. You can see that it's just a definition of conditional probability, right? So, and I just added logs. That's why there is a log and something minus. Okay, now what we're going to do, interestingly, is we're going to take an expectation of this whole thing with respect to, okay, we'll take an expectation with respect to the probability of zm given z and theta. Okay, yeah, you see left hand side has nothing to do with theta, left hand side has nothing to do with theta anyway. Left hand side is also nothing to do with zm. So if you take an expectation with respect to a random variable, and the left hand side has nothing to do with that random variable, zm is something different, right? Deltas, let's say, and z's are y's. So there is no expectation of something with respect to another random variable. It's a constant, so expectation is just gone. Okay, so left hand side, if you take an expectation, it's the same. So this is the what we care about. Okay, let's call it, let me just call it L. Okay, and right hand side, it's not so clear. So theta is different, but if you take the expectation of zm, there is a zm here. So if I average out, if I bring these probabilities times that log thing and sum, there is still, you can't just remove that expectation. Okay, so, or in other words, let me put explicitly what the expectation is: sum over probability of zm given z theta times log of z zm given theta prime. Okay, this is the taking expectations on both sides. First, left side, it doesn't matter. Right side, this is the expectation, minus sum over zm probability of zm given z theta times log of probability of zm given z theta prime. Okay, right? I just added that expectation, explicitly written expectation, but this first term is actually the let's call the first term q of theta prime and theta, and let's call the second term r of theta prime and theta. Okay, because zm's and z's are, I mean, z is anyway data, so that's fixed. There's nothing changing with z. Zm is a random variable. I'm averaging out every single value, so it's zm doesn't appear. I mean, averages out. So the second term is function of theta prime and theta. The first term is a function of theta prime and theta. Okay, the first term is what is we are maximizing in the m step of EM algorithm. So in the m step of EM algorithm, literally that's what I wrote: some averaging of zm given z at some previous value, okay, theta naught, of a likelihood function, right? So that's that likelihood function. This is the likelihood function, log of, I guess, probability. Yeah, so that's the likelihood function. So that's that term q is being maximized in the m step. Okay, and there is an other quantity r. Okay, so what we care about is this thing. Let's call it L. We care about maximizing L as a function of theta prime. Okay, we care about maximizing L as a function of theta prime. That was hard to do. So what we are actually maximizing is in the M step, we are maximizing at least Q as a function of theta prime. Okay, so where theta, think of it as previous iterate value, previous theta naught or whatever. So we're only maximizing this. There is another term which we left out. Okay, we're only maximizing the first term in every step, every EM iteration, but we are saying that we are able to maximize the likelihood, which is the left hand side. Okay, so we'll try to reconcile this issue that we are supposed to maximize the left hand side, but we're only maximizing the first term of the right hand side. So there is a gap. And the way we'll reconcile is to show that, let's say the previous value was theta, in the sense that the previous iteration value was theta or theta naught, okay, in general theta. I'm going to theta prime, okay, in the EM algorithm, which means that theta prime is the maximizer, okay, in the M step, okay. Then what I want to show is that the likelihood at theta prime minus the likelihood at theta was the previous value, okay, which I can evaluate my likelihood even at theta as well. I'm going to show that this is positive, which means that my likelihood with the next new candidate has actually increased. Okay, that's a cool thing. So I want to show that as I'm doing one step of EM iteration, my likelihood is going to increase. Okay, my likelihood of my data, the left hand side, is going to increase. Okay, that's what I want to show. Inside the EM, something else is happening. There's an E step and M step is happening, but I want to show that this is at least likelihood is increasing as a function of my new parameters. Okay, to show this, I want to show that Q of theta prime on theta minus R of theta prime on theta is greater than 0. Sorry, not just this actually. Minus, okay, this is just the first term at theta prime. L at theta is actually just Q of theta and theta minus R theta and theta, right? So instead of theta prime as a variable, I just put a specific value theta. So this I want to show is greater than 0. Okay, which is the same as Q, okay, theta prime comma theta minus Q of theta and theta minus plus R of theta and theta. Okay, is this? Yeah, this is fine, right? Okay, this part is actually greater than 0 because theta prime is the maximizer in the M step. So for any other theta, Q value has to be higher, lower. Okay, so all I'm saying is that the first term, M step is actually taking care of it. M step is actually giving me the best theta prime. So any other first coordinate value I pick doesn't matter. So the first difference between these two is greater than 0. So all I want to show is that somehow, not this underline, but including the negative sign, let's say, is also greater than 0. That's what I want to show. Okay, and so what we want to show is minus R of theta, I guess prime theta, minus R of theta and theta. This thing is greater than 0. Okay, so what is R actually? R of theta prime and theta is, what is it? Is some expectations, right? So let me just write sum over some random variable. Let's say, realization is a random variable. Let's say it's I of Let me use Ri, something like Qi here. Yeah. So R of theta prime comma theta is just some summation, some averaging. Okay. Actually, if you want the exact expression, it's sum over Zm of P of Zm given Z and I think in this case theta times the log of the probability of Zm given Z and theta prime. Okay, that's a messy expression, but all I'm saying is just think of this as Ri's, just think of it as Qi's, and these are I's. Okay, in the sense that as a Zm is like deltas and it only takes two values, so I is 1 or 0, and for each one there is a probability associated with it. Okay, two different distributions, that's all. One is parameterized with theta, and the other one is parameterized theta prime. Okay, and R of theta and theta is just sum over, in this case theta, right? So what was the thing corresponding to theta? So Qi log Qi. Okay, I. So this difference is actually, let's call it okay, the difference is actually minus of sum over I Qi log of Ri divided by Qi. Okay, where Ri, think of Ri and Qi as like some probability mass function. In the two-dimensional case, something like this: I is equal to 0 and 1, 0 and 1. Let's say this is Q distribution, and this is R distribution. Okay, so we want to show that this is greater than 0. Okay, I just I'm using a few notation changes, but if we can show that this is greater than 0, then we are done. That which means that every iteration of EM we are increasing the likelihood that we care about, which is the left hand side. Okay, now how do we show that this is positive? So this is positive is the same thing as showing sum over I Qi log of Ri by Qi is negative. Okay, it's the same thing as showing this. Okay, this is negative irrespective of any Qi distribution that I pick. Oh, sorry, this is not correct. Any Ri distribution that I pick. Okay, because that's the one inside. So theta prime is what I'm changing, right? In the theta prime is the variable. Theta is something that I got from the previous iterate. Okay, so I want to show that this term is anyway negative, or the previous, this thing is either always positive and this thing is always negative. I want to show that this is negative for any value of Ri. Okay, and if I want to show that this is always negative for any value of Ri, if I maximize this guy with respect to Ri, okay, and show that the maximum value is negative, then any value of Ri will also give me a negative value. When I say Ri, it's just R is the distribution, probability mass function. Okay, and you can actually do that. So I want to show that max over Ri of sum over I Qi log of Ri by Qi subject to sum of Ri is equal to 1. This thing is less than 0. Okay, the objective value is less than 0. I mean, subject to this is because Ri's are supposed to be distributions, right? I mean, R's and Q's are supposed to be distributions, right? So how do you solve this? You can take the first derivative with respect to, you can take the derivative set it equal to 0. It's a constraint problem. So the way you do it is to bring in what is called a Lagrange multiplier. Okay. So sum over I Qi log of Ri by Qi, it's a minus lambda sum over Ri minus 1. Okay. So you take the derivative with respect to several things. First with respect to Ri, and second with respect to lambda. With respect to lambda, you get the same, which is if you take the derivative with respect to lambda and set it equal to 0, implies sum of Ri is equal to 1. Right? The first term doesn't involve lambda. The second term involves lambda, but derivative of lambda with respect to itself is 1. So sum of Ri is equal to 1. That's the derivative with respect to lambda. if you find the derivative with respect to Ri, all the terms except for the ith term cancel. I mean, they're not functions of Ri, so they'll drop out. This is going to be Qi divided by Ri. Okay, so log of Ri, if you take the first derivative with respect to Ri, it's 1 by x. Log of x is derivative of log of x is 1 by x. Okay, that's Qi by Ri, and you'll have minus lambda. One of the Ri's is also here, is equal to 0. Okay, so that's what you get here. From the derivative with respect to Ri, you get this. Derivative with respect to lambda, you get this. From these, you can see that Ri is equal to Qi is the best choice. Okay, because if Ri is equal to Qi, then sum of Ri is also 1, because Qi is a distribution, and sorry, not this. So Ri is equal to, yeah, and Qi by Ri is equal to lambda. Okay, but you'll see that lambda is equal to 1. So okay, if you want me to do it, I can do it. So sum of Qi, where is this? So let's say Qi is equal to lambda times Ri. Sum both sides. Sum of Qi is equal to lambda times sum of Ri. But we know that sum of Qi is 1, and sum of Ri has to be 1. So lambda is equal to 1. Okay. So anyway, all this laborious exercise only to show that this thing, it's maximized at Ri is equal to Qi, this objective function with some constraint. But when I substitute Ri is equal to Qi, log of Ri by Qi is just 1. Log of 1 is 0. Okay, so then the objective is 0. So the highest value that this function, this objective value with that constraint can take is 0. Okay, so we didn't show it's greater than 0, or so we didn't show it's less than 0, but I guess less than equal to 0. We showed that it's equal to 0 at the highest guy. So at a given arbitrary Qi, we don't know. I mean, it will be definitely less. Okay, so that's kind of summarizing the whole EM. So we went with, okay, maximizing likelihoods for multimodal distributions is hard. Let's look at the EM algorithm, which is basically looking at previous iterates, previous theta, previous parameter values in the M step, in the E step, getting predictions of what would be the likely values of the hidden variables, or the things that we hallucinated about, deltas in the previous case. Given that, we can maximize some sort of a joint likelihood, which is easy to maximize. Okay, and we get a new parameter estimate theta1 and repeat the loop. Okay, we repeated that, and it came, let's say you repeated it 1,000 times, you got some parameter. Now in the last few minutes, we saw that EM actually maximizes only the Q term, but just maximizing the Q term in each iteration is enough, because is enough to increase the likelihood, at least locally. Okay, in each iteration it increases the likelihood of the thing that we care about. Okay, by showing Q term increases every round, and R term is never going the opposite direction. Anyway, so that's EM. So right after, so what is the time? 7:30. Wow. Okay. So let's take a break for 8 minutes and come back at 7:40.
No, it's you speak about it differently, so it's helping.
Okay. Okay, so let's switch gears. So the first part was about maximum likelihood estimation, right? So now we're going to actually look at something else, which is more Bayesian. Okay, so we're going to look at sampling. Okay, so what is sampling? Sampling is, of course, you've seen, like, let's get a sample from a distribution. So we've seen that version, but where is it applied, right? There are many applications, but one application could be what is called, if you want to generate an article automatically. Okay, so you want the computer to write an article, right, or a passage, or a paragraph. Then how do you go about doing it? Okay, so you build what is called a language model. Okay, so some of you have done text analytics. Some of you, yes. Some of you have not done text analytics. So just think of it as, you have a corpus of text. Okay, so maybe all the Wikipedia articles, or your newspaper articles. Then you use that bunch of the whole corpus to compress it into a model. Okay, it's called a language model. It's not a I guess a direct supervised learning problem, but you can make it one, in some, we'll not go into the details, but let's say you build a language model, okay? You can use such a model to generate new text or new paragraphs, okay? But while generating, you don't want it to be deterministic, it should not generate the same text again and again, right? So you need to generate something different, and so you do sampling, okay? So you can generate from some sort of a probability object that it maintains, essentially some sort of conditional distribution or some joint distribution. You get new samples, and the new samples correspond to maybe new words. Maybe now you've maybe generated 3 words, and given that context, given the 3 words, the language model will take that as an input and generate or sample. You sample another word, and that will be the 4th word, and so on. Hopefully, it looks like an actual sentence, and there are several models that have been developed in the natural language processing community which actually do this, okay? At least for really short sentences, maybe not full paragraphs or articles, but short sentences or things like reviews and so on, you can automatically generate it, okay? So that's one example of just why do we need sampling. This is for variety, getting variety. In general, for example, for the Gaussian mixture model that we saw in the previous part, right? So we had Gaussian mixture model. How do you sample from a Gaussian mixture model? We know that the distribution is like this. Maybe has 2 modes, 2 peaks, and it has parameters, mu1, mu2, sigma 1, sigma 2, and pi. How do you sample from this? Okay, I want to sample from this. Any ideas? Any idea? How? Let's say you've only been given access to sampling from a Gaussian, but you don't know how to sample from this. Or maybe you've only been given access to a Gaussian and maybe a Bernoulli. Then how do you sample?
If say another V2 is greater than V1, then it compute the difference between V1 and something like that. Space or the space.
Yeah, thinking about it, you are in the roughly the right direction. So basically, you remember the generative point of view I said? So that's a way to figure out sampling as well. So first you sample a Bernoulli. Maybe it lands heads or tails. If it lands heads, then draw a sample from the left side Gaussian, for example, and you get a sample. That's it. And if it lands tails, you get a sample from the right side Gaussian, you get a sample. That's it. Okay, so that's a way to, the generative model is a way to generate essentially samples. Okay, I mean not just that, but that's a one way to generate samples. So generating samples from this type of distribution is easy. Okay, if you have access to getting a sample from a Bernoulli and a Gaussian. Okay, but in general, okay, there could be more complex distributions. Okay, so if you use Bayes rule, okay, if you use Bayes rule, which is what? Which is so think of ridge regression, right? So in ridge regression, let me just say, okay, I said this is actually here the generative point of view is that beta is normally distributed. Beta is a vector here. Is normally distributed with mean 0 and some variance, maybe let's say tau square times I, and y is also normally distributed with mean beta transpose, let's say x, and with some variance sigma square I. Okay, so or if y is one dimensional, then it's just without the I is 1 cross 1. Okay, so ridge regression is actually something, ridge regression, we have a residual sum of squares objective and then the 2 norm square term, right, regularization term. But we also saw actually before that if you assume beta is normal and y is conditionally normal given beta, so y condition and beta, sorry, is normal, then if this is true, then the probability of beta given y, okay, this is the posterior distribution on beta, okay, this is equal to probability of y given beta times probability of beta divided by probability of y, right? This is Bayes rule, right? Now I just told you probability of beta, we just said what is that. Probability of y given beta, we just said what it is. Probability of y itself is basically integration or probability of y is equal to little y and beta is equal to something over all beta values. Okay. Yeah. Integrate out the second part. Okay. So this is base rule, and you get a posterior distribution on beta. Okay. And we saw that the MAP, maximum a posteriori prediction, or MAP estimate, sorry, a posteriori estimate, not prediction. MAP estimate is basically maximizing the numerator, because the denominator has nothing to do with marginalizes out beta. So we just care about I mean, it has nothing to do with beta. So the numerator has something to do with beta. There are terms, beta terms involved. This is the posterior distribution over beta. Okay, given y, which y is the data. Okay, MAP estimate would be the most likely beta value or beta vector value. Okay, that's what maximum posteriori estimate means. Okay, how do we get the most likely beta value? We maximize the posterior over all values of beta. You know, posterior is a distribution. For every given value of beta, it will evaluate to a number, right? So I'm trying to figure out what is the beta that maximizes the posterior. That's map estimation. Okay. MLE estimation would not have, would be just maximizing the likelihood. Okay, that would be just residual sum of squares. If you're maximizing just the term in the box, that would be MLE estimation. This is map estimation, but map estimation is saying most likely beta value. So beta is actually a random variable. It has a posterior distribution. Okay, this guy. Okay. So instead of finding the most likely beta value, I could do other things. If I have a posterior distribution on beta, I can sample the beta from it. Okay, that sample, may correspond to likely values of beta, and with low probability will correspond to unlikely values of beta. Okay. So this is a Bayesian world where you think of your, in this case the beta, you are assuming that beta could be any vector, maybe with a some prior. Sorry, actually, beta could be a vector with actually mean zeros, and you have a prior on it, and you observe some data, and you have a posterior distribution on what the values the vector beta takes. Okay, it's a Bayesian view, and if you want to compute any function of beta, then if you want to compute any function of this posterior distribution, any function of beta, let's say, then what you do is, for example, the norm of beta or something like that. So any function of beta, or for example, actually, let me just, not norm of beta. Let's say I want to make a new prediction. Okay, beta transpose x test. Okay, I want to make this prediction, but I don't know which beta to pick because there is a distribution over beta. So I can actually pick, right? I can actually pick. I can integrate this with respect to the posterior distribution of beta, given whatever this posterior. In the previous slide it was y, but it's the same thing. I can integrate it over betas. Okay, so this would be my averaged prediction. Okay, instead of finding the MAP estimate beta and then just taking beta transpose x, I can do this as well. But in ridge regression, it turns out that because the prior is normal and the condition, likelihood is normal, the posterior is also normally distributed. So you can just work with the mean, which is also the most likely beta hat in the map problem or in the posterior. Okay, for ridge regression, it's not an issue, but in general, if your likelihood was something else, instead of normally distributed, it could be some other distribution, maybe gamma distribution. Maybe y's are not values which take negative values, y's are only taking positive values. Then maybe you would assume that it is gamma distribution. Then the posterior is not going to be normally distributed. It's going to be some messy object. Okay, you have to really do the base rule to get the posterior. There's no way around. There's no manual, hand computation you can probably do to reduce it. Okay, and then if you want to find this, you really need to sample a bunch of betas. You can actually find this by doing I sample a bunch of beta values, maybe beta 1 to beta 100, then I can take those beta values and approximate this integration with that beta value. So although I have this posterior distribution, I can get a bunch of samples, in this case 100 samples, and approximate this integration with that. Evaluate each sample and average it, and actually take 1 by 100, let's say, and that's the average. So this is another example of where sampling could be used. Yeah.
Is there any kind of upper bound to know how many you should sample for data to get temperature prediction?
Yeah. So the question is there any information about how many samples to take to get a good approximation? So this is an approximation, squiggly equality. So there is So there is a, if you take a bunch of samples. So this has nothing to do with, I guess, it's kind of tangent to what I'm going to discuss. But so if you get a bunch of samples and you take a estimate from it, like you got a bunch of samples and take an estimate, because you can think of the original 100 examples as random variables, and so now you have a derived random variable. We can talk about how different this derived random variable is from let me rephrase it. So you're asking whether how far is this estimate? So you're asking the difference between this is small or not. How many samples do I need to ensure that the difference between these two is small or not? So that is actually doable. How good is that approximation? So there are technical ways to show it. It's just that I don't remember the exact names of methods, but these are actually quantitative versions of, I guess, what are these called? Law of large numbers.
I think MCMC.
We'll get to MCMC right now, but right here, if you're asking if the average is, how good is this average compared to this integration, it's basically just, this integration is nothing but, this is the actual expectation, right? This is the expectation. You're asking, this empirical average, how far is it from the expectation? That's just that can be reasoned by saying that if you have lots and lots of samples instead of 100 million, then by law of large numbers, it's actually the same as expectation for most cases. And you can also have quantitative versions of it, like how many samples needed to get to 0.1 error on your estimate. That also can be answered. Sorry, I took a few minutes to answer that, but so anyway, I was just trying to motivate why you would need sampling. Sampling. So we'll directly get to, so sampling is difficult generally. Like as I said, if y's were, instead of this normal distribution, if you had a gamma distribution here, which is some other name, for positive valued random variable, then the posterior would be messy. You can't really evaluate it. I mean, you can evaluate it. You can, posterior will be messy, but you can't also easily integrate it, do integration with respect to it. So you would like samples from the posterior. That's just for this prediction problem. But in general, you can have a probability joint distribution between several random variables. Let's call it u1 to up. Which means that capital U1 takes a value little u1, capital U2 takes a value little u2, and so on. Maybe p such p-dimensional random variable, so p-dimensional joint distribution. So I want to get a sample which is little u1 all the way to little up. Is that the notation? I've changed the notation, but so let's say I want to get the sample. How do we get it? It's not clear. For the Gaussian mixture models, we said it's easy, but here it's difficult. So there's a way to get the samples using this whole family of techniques called Markov chain Monte Carlo. Monte Carlo is just, for example, this is called a Monte Carlo average, by the way. The Markov chain part I'm going to quickly explain, but we can do this. We can get samples from any complex distribution using MC techniques, and the specific technique that we're going to look at today is called Gibbs sampling. Okay, and it can generate samples from this joint distribution as long as it has access to the following object, which is the conditional probability of ui given everything else. So in this case, u1 to ui minus 1, ui plus 1 to up. Okay, if I have this for every I. Okay, so Gibbs sampling can generate samples from this messy joint distribution as long as I can get samples from this one-dimensional conditional distribution. Okay, so as long as Gibbs sampling has access to this, it can generate samples for this guy, and the samples generation procedure has the I guess the backbone. So Gibbs sampling is a Markov chain Monte Carlo technique. Okay, there are many other techniques, Metropolis Hastings and so on. It works on the principle of what is called a Markov chain. Okay, is the objective clear? We want to sample. Sampling from distributions is sometimes hard. Okay, in particular, let's say there's a joint distribution between p variables, and we can sample it using MC techniques. And one of the techniques is Gibbs sampling. Now we'll get into the details of Gibbs sampling now. Any questions before that? No questions? Okay. So before I get to explain what a Markov chain is and so on, which is an explanation for why Gibbs sampling works, let me tell you what the procedure is, because the procedure is quite intuitive or straightforward, which is I'm going to illustrate it by an example. Let's say I have 4 variables. Okay, so u1, u2, u3, and u4. Okay, so I have a joint distribution between these guys. I want to get samples from this. Okay, and Gibbs sampling will work as follows. So let me start with some numbers. Okay, so 0, 1, minus 1, 2. Okay, these are, let's say the random variables are taking values on integers, negative integers and positive integers. Let's say that's fine. Okay, let me start with some initial values. Okay, then what I'm going to do is the following. So I want to create, what I'm going to do is I'm going to create the next sample. So this is the 0th sample or observation. This row is the 0th sample or the observation, this whole row. Okay, now I'm going to create the first sample, in this case, first sample, entry wise. So I'm going to first create little u1, some value for little u1, and then I'm going to create the next entry, and then I'm going to create the next entry, and then the next entry. Okay, so the first entry I'm going to create by drawing a sample from little u1. So probability of u1 given u2 is equal to 1, u3 is equal to minus 1, and u4 is equal to 2. So where did I get 1, minus 1, and 2? Okay, 1, minus 1, 2 are just the previous row entries, and those for u2, u3, and u4. Okay, just understand the procedure first, mechanics of the procedure. We'll talk about why this makes sense later. Okay, so I'll get a sample from here. Maybe it's value 3. Okay, from this probability. Now the next number, I'm going to find the probability using probability of u2 given u1 is 3, u3 is minus 1, and u4 is 2. Okay, because I told you Gibbs sampling needs access to this in each dimension conditional probabilities, conditional probability of the given coordinate given everything else. Okay, if I have access to such objects, then I can sample from the full distribution. Okay, so I'll draw sample from here. So this entry would be, let's say, minus 5. Okay, and similarly you can see some pattern here, right? So the third, when I sample this guy, I'll use 3 and minus 5 from the current row and 2 from the previous row, and I'll get some entry here. Maybe again, I don't know, 0, and so on. So you continue this, okay? So you continue over several rounds, and in each round, the new sample that you're creating, new sample's coordinate that you're creating depends on how many numbers, previous p minus 1 numbers, so previous 3 numbers, because it's, it's 3 other coordinates are there, so 3 other numbers, okay? Right? Yeah.
I have some more general questions.
Yes, go ahead.
About this. So this is the purpose of this is you're given the distributions of these U1, U2, U3, U4, and you're trying to generate a sample set.
Yeah, I've been given P of U1, U2, U3, and U4, but I don't know how to generate a sample from this.
So you don't have data.
Computationally.
You've been given this.
Yeah, let's say it's parametric.
And what's the purpose of generating the data from those? What would you use that for?
We went through a couple of examples, right? Language models was about generating new text. So even if you knew this language model, which is essentially this joint distribution type of a thing, or conditional distribution type of a thing, you don't know how to generate new words. I mean, unless if it's something simple like Bernoulli or random, the function calls, right? NumPy dot random dot random or whatever in R as well, random. But beyond simple distributions, one-dimensional distributions and so on, it's not clear how to generate samples, okay? Because the motivating example was like ridge regression. Instead of this normality assumption, if you make a gamma distribution assumption for an outcome, for example, it cannot be negative. For example, income cannot be negative or something. Tax value cannot be negative. Then the posterior distribution on the parameters of this problem would be some weird distribution. Okay, if it's a mixture of Gaussians, we just discussed that it's still okay. But if this weird distribution, we only know how to evaluate. It looks like a messy mathematical formula. Then it's not clear how to get a sample from that. We know exactly p of x is equal to something, some e to the power something times sine of something else and so on. Could be. You could even have an analytical formula, but you may not be able to generate a sample from it. Okay. Language models, for example, regression, for example, not maybe ridge regression, because ridge regression you already know how to do it. What other examples? You'll see, I don't know how many of you have heard of these things called generative adversarial networks. No? Okay. There was this a lot of publicity around people generating new faces. This face does not exist or something, right? What is it? Yeah. So it's something to do with neural networks, but ultimately, this recent research has created this object where you can generate faces. Okay, there's a distribution over photographs of faces of people. It's very faces of people. How do you represent? Think of them as images. Okay, pictures, photographs. Think of a distribution over these photographs. It's not even clear how they are placed. Numbers at least we can understand. Okay, on the real line and so on. You have a distribution over photographs, and then you want to sample a new photograph. Okay, and that photograph need not be a database lookup of somebody else already existing. That photograph could be somebody who does not exist in this world. Okay, so. So people have created some objects called generative adversarial networks to create these, and these are useful for things, for example, in that case, maybe useful for animation or things of that nature. But you can do that. I mean, this is parametric sampling, where you know the posterior distribution, you want to get samples. Where you want to compute, you have a random variable, you want to get samples, and then you can compute functions of it easily using this Monte Carlo averaging. Okay. So Gibbs sampling is just this. You do you get sample coordinate wise, or coordinate wise, and for that you just need these conditional probabilities. Okay. So you see that this point, this whatever number here is, let's say this is 5, it only depends on the previous 3 numbers. Okay. So this is actually a Markov property. Okay. What is the Markov property? It's just the probability of a random variable, maybe z100 given z99, z98, z97 all the way to z1. Maybe it is equal to probability of z100 given z99, z98, Z97, let's say. Okay, so this is an example of a Markov property. And by Markov, it just means that given history, maybe I've generated these samples. Maybe the first, let's say these are those U1, U2, U3, U4 vectors. Let's say, given all these my 99 previous observations or samples, when I'm creating the new sample, I only need the previous 3 observations, for example. Okay, Markov property is just a memoryless property where I'm saying that given the immediate previous information, all the information that led to this point is irrelevant. Okay.
But we are here considering 98.
Okay, these are not observations. Think of them as like the coordinates. Okay. Okay, his question is, okay, so in the previous example we are not really talking about, so we are talking about relying on only the previous 3 coordinates, not the previous 3 samples or observations. Okay, yeah, so but in general, what is a Markov property is just that given history, so let's call this history, it only depends on the most recent point in the history or most recent k points in the history or whatever. Okay, so that's called Markov property. It's a memoryless property where you don't need information from before to figure out what is the likelihood of Z100 taking some value and so on. Okay, so this is called a Markov property, and so okay, that's Markov property. And if you look at the Gibbs sampling procedure, I'm creating these samples in an iterative way given access to these guys. Now you can see that these there is dependence across samples, right? Because when I'm creating this sample, when I created this 3 minus 5 0 and something else, it depended on the previous observation. In the sense it depends on the previous numbers, because 3 needed these 3 numbers, minus 5 needed these 2 numbers, and so on. So there is dependence across time. So these are not independent samples. So if you draw a sample from a Gaussian, maybe you'll get independent samples every time you call random. Okay. Actually, in computers, things are not really random. There is something called pseudo randomness, where it's deterministic numbers from which you get these Gaussian observations. But here, anyway, that's a tangent. Here, the observations are not independent across time. Okay, they're not independent across time, but the Gibbs sampling, guarantees that eventually the samples that you're constructing. So this is some constructive procedure, right? How do I know that I'm only sampling from these conditional probabilities? How do I know that I'm actually getting samples from the joint distribution, right? From the joint distribution U1, U2, U3, U4. It's not clear. By just sampling from these conditional distributions in this particular way, it's not clear how I'm getting samples from the joint distribution. But Markov or these Markov chain Monte Carlo methods, there's a guarantee that eventually they will actually generate samples from the target distribution. I guess this is called the target distribution. Target. So you'll eventually start generating samples from the target distribution. Although they're not independent across iterations or across samples, there will be samples from the target distribution. Okay. So why is there such a guarantee? And for that, we need to understand the notion of a Markov chain. And I'm going to be extremely short and hand wavy here. We'll not go into the gory details of Markov chains. What is a Markov chain? Markov chain is a what is a Markov chain? Okay, I'll illustrate by example. It's easier that way. So so Markov chain is a object which tells me if I am in if I currently take a value which is like the circular nodes, they represent what value I currently take. Okay, so think of a random variable x taking a value 1 currently. Okay, then a Markov chain just tells me what is the probability with which it will take a value 2 in the next step, or probability, what's the probability with which it will take a value 0 in the next step. Okay, so from 1 I can go to either 0 or 2. Okay, there's a probability associated with me going to 0 or 2. Okay, so that's just a conditional probability that let's call it x1 is equal to 1, then the probability of x2 is equal to 0 given x1 is equal to 1, there is some number, and probability of x2 is equal to 2 given x1 is equal to 1, there is some other number. Okay, so Markov chain is just characterized by these conditional probabilities. Probability given the current value, what is the probability of taking the next value. Okay, it's a chain because it's a graph with some these edges. Okay, and think of this, they're only, and these are called states. Okay, these are 3 states here. So essentially I can talk about this whole this Markov chain with 3 states using what is called a transition probability distribution. Which is going to be a 3 cross 3 matrix, where I'm saying if I start from 1, there's 0 probability that I'll stay in 1 in the next round in this case, and maybe with some probability A I'll go to 2, with probability B I'll go to 0, so B and A. So this is 1, 0 and 2, it's messed up, but each row corresponds to the conditional probability of me going to some the next value, taking the next value. Okay, so that's it. A Markov chain is just a bunch of values, and what is the probability that given the current value, what value I'll take next. Okay, I mean this is the simplest case. There are many variations of Markov chains, but this is a Markov chain. And the cool thing about this is that if you start from some value, let's say x1 is equal to 1, and keep jumping around these states, according to this probability, this transition distribution, I guess, matrix. Okay, where each row just corresponds to the conditional probability. Okay, each row is a conditional probability. If you keep jumping around, you will keep getting a bunch of values, right? Maybe 1 to 2, 2 to 0, 0 to 2 again, 2 to 1 again, and so on. You will get a bunch of numbers. If you draw a histogram of these numbers, in this case 0, 1, and 2, okay, it will settle on something called a stationary distribution. Okay, all I'm saying is, I just described the Markov chain as a bunch of values and jumping around them using this matrix. Using the matrix you do a transition. If you keep jumping around, all I'm saying is, and if you look at the histogram of the values that you're getting, you get a sequence of numbers, right? So you just look at a histogram of them. They will correspond to a distribution which is kind of doesn't change, in the sense that there'll be some distribution that you'll get, some sort of limiting distribution that doesn't change across time. That's why it's called stationary distribution. Okay, and I mean it may not always be there and so on, but in general there's a stationary distribution. Okay, and so which means that if I okay, that's fine. So there is a stationary distribution if you keep sampling. I don't want to talk about further properties of how the stationary distribution is related to this matrix. So I started with the matrix. I told you the matrix corresponds, if I keep sampling and keep jumping around, I'll get to a stationary distribution. Okay, so there are 2 objects. So there's a transition density matrix, let's call it Q, and there's a stationary distribution P. Okay, there are 2 objects. Q implies P. Eventually, if I keep doing something with respect to Q, I'll get to P. Now that's a Markov chain in the most simplest idea. Now in Gibbs sampling, the stationary distribution corresponds to our target distribution. Okay, so we want to think of some Markov chain. We don't know what the states are. I haven't told you what the states are. I haven't told you what the Q is. But irrespective of I'll tell you what the Q is and what the states are. It should, if I keep sampling if I keep jumping around a particular chain, I haven't told you the details of the chain, I have to get to a distribution, the stationary distribution, which is actually the target distribution that we care about, that P of U1, U2, U3, U4. So this is our target, right? So we want this as a stationary distribution. Okay, and it turns out that this procedure of sampling, Gibbs sampling, of sampling from each coordinate given every other coordinate, is a way to transition, it implicitly defines the Q. Okay, so which is the transition density matrix. So this transition distribution matrix is defined by this procedure of going from one sample to another. Okay, using these conditional probabilities. Okay, so Q is this procedure of going from one sample to the other, and if you do this enough times, you are getting samples from the actual target, because the target is the stationary distribution of this procedure, and this procedure is capturing that Markov chain. Okay, what are the states of this Markov chain? If you're curious, the states are all the values that U1, U2, U3, U4 can take. So let's say U1, U2, U3, U4 can take 10 different values each, right? Then let's say -5 to +4. Then the states of the Markov chain are all the values, all the 4 tuples that the random variables can take. Okay, so there's some sort of a transition from all the each 4 tuple to another 4 tuple, such that you keep jumping around it, which is what we are doing by from one sample to the other. That's what we are creating. Okay, they are dependent, clearly. Okay, the new sample depends on where you came from. They're dependent, but eventually, after enough times, there will be a stationary distribution, and that stationary distribution, because we are sampling according to these underlined conditional probabilities, it corresponds to actually the target distribution, which is the joint distribution of U1, U2, U3, U4. Okay, so the way that people came up with this algorithm is, of course, knowing the Markov chain technology, idea of Markov chains, and to know that, okay, we want this as a stationary distribution, the target distribution as a stationary distribution. What should we do? What is the transition probability object we should create such that we can get to this stationary distribution, which is the target distribution? Okay, and that's led to this particular algorithm. There are many other algorithms with different procedures, but they all correspond to some way to get to the stationary distribution, which is on the top right, I guess, to this guy. Okay. I will not go into the details because there are several details I skipped, and there's no details in the lecture notes anyway. In the last, so is there any questions about sampling and Markov chain Monte Carlo methods? So Gibbs sampling is just one example in this family of methods, and there is an underlying thing called a Markov chain. Because we haven't spent any time on Markov chains, this is the simplest, I guess, intuitive idea around it. Any questions? In the next, I guess, 2-3 minutes, I just want to kind of tell you where we're heading now. So actually, the lecture before the exam and now, we kind of thought about maximum likelihood estimation. Okay, we just kind of stopped thinking about supervised learning and started thinking about maximum likelihood estimation in general. It could be fitting a Gaussian, fitting a mixture of Gaussians, or whatever, right, to data. And sampling is related to once you fit a distribution, or sampling. If you have a distribution, you want to get samples to estimate means and functions of those random variables, then you can do sampling. Okay. Now we again, in the next few lectures, we're going to go back into the world of supervised learning, and this time we're going to focus on all sorts of nonlinear methods. So random forests, support vector machines, boosting methods, gradient boosted decision trees, tree methods, right? Cart and regression trees and so on. All those are nonlinear. Okay. We're going to look at again supervised learning, and then hopefully in the last part of the course we're going to look at some unsupervised methods like clustering and spectral clustering, usual clustering, I guess, and association rules, and maybe time series analysis at the end. Okay. Right now, in the next 2-3 minutes, I'm going to talk about generalized additive models. Okay. And special case of this is generalized. Generalized linear models. Okay, these are now again back to supervised learning land, and I'm just going to give you a couple of. This is something that you already know. That's why I'm only spending 2 minutes on this. So generalized additive models just mean that we're going to assume that the conditional expectation of y given x. Okay, let's say we're doing regression. I mean, for us, regression classification, we saw that it's almost equivalent to each other. So conditional expectation of y given x is some constant plus f1 of x1 plus f2 of x2 plus fp of xp. Okay, so that's generalized additive models for you. Additive because there's additions across features, and for each feature there's some arbitrary function of that feature, like a log on one of the features, maybe x square, x1, x2 square for one of the features, for the third feature maybe something else, and so on, some transformations. Think of these functions as some transformations. Okay, then this is not a, I guess, a vanilla linear model. It's generalized, and that's why it's called generalized additive model. Okay, there's really nothing going on here. It could be that you don't know what the function is. Maybe it's ax, a1 x1 plus a2 x1 square plus a3 x1 cube. Okay, then you have to find these coefficients. For example, if the function f1 of x1, if this is f1 of x1 is this, then hopefully using training data you can estimate these 3 coefficients. Okay, that's all. I mean, otherwise there is nothing going on. So that's the generalization. So each coordinate wise you can have arbitrary function, and we have seen this. We can have interaction terms. We have already seen those things. So this is something. It's just a recap. Okay, when people say generalized additive models. And the second thing is generalized linear models. Okay, so this conditional expectation of y given x, we can either say that this conditional expectation of y given x, let's call it mu. Okay, either we can say that mu is equal to that thing, which is c plus sum over I fi xi, or we can also generalize the left hand side by saying, okay, it's not mu, maybe it's e to the power mu, which is equal to c plus sum over I f of I xi. Okay, we are now transforming the left hand side. Okay, so basically we are saying that it's not the conditional expectation of y given x which is linear, but for example e to the power that is linear, or it could be even log of mu which is linear. Okay, so these functions log, e, these are called link functions. Okay, these just think of any transformation. Like if you had y's, you do a transformation on the y's. Okay, and that transformation is generally called link function. Okay, and this is generalized linear models for you. There's a particular link function for, so when you do logistic regression in R, you use LM, right? Or yeah, when you do logistic regression, you're assuming that the conditional probability of G is, let's say, 2 binary logistic regression, conditional probability of one of the classes given x is equal to x divided by 1 minus the conditional probability of G is equal to 1 given x is equal to x, log is linear, right? Something like beta transpose x. This is logistic regression assumption, right? The log odds ratio, this, let's say, binary case, is linear, right? Now, for classification, just think of this as mu instead of conditional expectation of y given x. This is just a conditional expectation of G given x. Okay, that's what this is. In a binary classification, this is what it is. Then log of mu by 1 minus mu is linear in this case beta transpose x. Okay, some linear function. So this is called a logit transformation. Okay, so you're saying that whatever mu is, mu is just the, this is nothing but, okay, not this, but expectation of G given x is equal to x is mu, is the same as before. Conditional expectation of y given x is conditional expectation of G given x is the same thing for binary classification. I mean, this is actually equal. Sorry. So this is called a logistic transformation, and a few other transformations, probit transformation, where you do phi inverse of mu is equal to beta transpose x. So you're doing arbitrary transformations of the left hand side. Okay, this is called probit. It's called logit, and that's it. So that's generalized linear models. I didn't really spend too much time on it, but it's just transforming left hand side appropriately. Okay, and generalization of linear models is these models where you transform each individual features, bringing in interaction terms and so on. Okay, it's additive. It's still additive, but it's doing arbitrary transformations. Okay, so that's it for today. Next class we'll look at tree methods and tree methods mostly. Any questions? This one? This one. Okay, see you next week.